So a few weeks ago, I was at a plastic surgeons conference, and I got up here talking about accelerated aging. Nobody came. Lady after me was talking about preservation and anti-aging, standing room only. So I changed the title of my presentation to Review Accelerated Aging per ASTM F1980. And this is the -21 revision, happened in December recently, and there's a lot of focus on it and discussion about it because we're looking at humidity in relation to the standard, and that's the kind of the thing that's always been in the standard, but there's a bigger focus on it, and that's what we're going to talk about today. So we're going to actually dig into the standard a little bit. We're going to talk about the formula. We're going to dig into the variables and present the principles of accelerated aging. And the bottom line, of course, is patient safety. It's always about patient safety. And the data that we are going to ultimately end up with is going to be about real-time aging, right? We always have to back up our accelerated aging with real-time aging. And so in order to do that, accelerated aging is just really something for time to market, right? We're always looking for time to market, trying to get in a little bit faster, get our data, and then we back it up with real-time data. So in a sense, we don't even actually have to use accelerated aging. So this presentation today is going to cover a little bit about terminology. We're going to talk about stability testing, which is what we're really discussing today, relative to real-time, time versus temperature, and of course we're going to cover the changes in ASTM F1980. And we're talking about our sterile barrier system, and that's important to understand that when we're talking about the sterile barrier system, we're talking about the packaging itself, so that's what we're going to define that as. And we're also going to talk about the product, and that's a defining moment in this new standard. Is it's about, the title of the standard used to be Accelerated Aging of Sterile Barrier Systems for Medical Devices. It is now Sterile Barrier Systems and Medical Devices. That one little word changes a little bit of the focus. So stability testing, just to review, is found in ISO 11607, Part 1, Section 8.3, talks about stability testing and primarily talks first about real-time aging. And then it says you can use accelerated aging for the purposes of putting expiration date on, but ultimately you'll have to not redefine it, but actually define or follow it up with real-time aging. And then there's another portion of this, also found in 11607, that talks about package performance testing. And what I really want to bring out here is that your aging should be a separate entity from the package performance. And we're talking about package performance, we're talking about the transit portion, the shock, the vibe, the temperature, humidity, right? We have, oftentimes there's an environmental component of the package performance testing. So we're separating that out as package performance testing or performance testing and the accelerated aging. And those should be separate entities. And we'll talk about some another guidance document that kind of covers that as well. So package performance testing evaluates the interaction of the package for a variety of different, what we call hazards. Manufacturing, sterilization, handling, distribution, that's your vibration, that's your drops, that's what we're talking about. So after the aging portion, so we're jumping back to the accelerated aging, after the aging portion, we have sterile barrier systems that have been subjected to higher temperatures, higher elevated temperatures, maybe, and humidity is often uncontrolled. That's the premise, that's the basic premise of previous tests that we've been doing. And then it has to be evaluated. So how do we evaluate the packaging after the aging? We use some tests, integrity tests, called gross leak or dye penetration. Then we look at some strength tests, and that's peel test or even burst test. And we're looking for changes in the packaging material. We're looking for changes in the sterile barrier system. And again, focus on the sterile barrier system, the packaging. And the packaging itself is independent of the physical configuration or the contents. Okay, what does that mean? It means that it doesn't matter what we put in if we're looking at, it's a frame of reference kind of thing. We're looking at the frame of reference of the packaging. So again, looking at the packaging, not really concerned about the contents. And this is what the original F1980 was about. It was mostly focused on packaging. So we could put tubing in there, we could put anything that we want inside. We could put a predicate, or not a predicate device, but we could put a device in there that doesn't meet spec and just use it for the aging purposes of aging the materials and get our data that way. So after looking at those types of the integrity of the packaging, you do the same thing for the performance end. So here we've jumped back to the performance of the packaging materials themselves. We've simulated a distribution environment. How do we know that the actual packaging has passed? You perform the similar tests. You perform the sterile barrier, gross leak, and peel testing. So let's talk more about the time versus temperature effect on the products. So we have, in the actual document itself, it doesn't recommend temperatures higher than plus 60 degrees C. And that's really because of nonlinear changes in the materials. So that could be changes in crystallinity, could be the formation of free radicals, or peroxide degradation in some cases. And these are this is the reason for the boundaries of not conducting aging greater than 60 degrees C. And we're focusing a little bit on the products now. So we're bringing kind of the product into the fold. Now, originally the test standard was focused on the packaging. Now it's and medical devices. So now we're looking at the products and the polymeric changes that can occur in the products. So here's the formula, really, of the accelerated aging portion of this. And what you're taking is the accelerated aging time, the actual time you're going to use to age your product, and you're going to divide it by an accelerated aging factor. And that's what we come up with in this example here. So you have the desired real time divided by an accelerated aging factor, gives you how many days you're actually going to expose the packaged product in the accelerated aging chamber, which is what you would see here in this photo. So how this all came about was there's this pretty smart guy, Savant Arrhenius, and he was actually a chemist primarily, but he focused on the aging factors of materials. And actually it wasn't materials, it was a single order degree of freedom system. So what that means is a mixture. You have two parts, and I mean, this is high school chemistry, right? You have two parts, put them together, you watch how fast they mix, you increase the temperature a little bit, they mix faster. That's his discovery, and that's the basis for this whole accelerated aging equation that we see right here. So you determine an accelerated aging factor, and the bottom line is, in general, for a 10 degrees C increase, you double the reaction rate. So we can use the inverse of that and say, well, if we elevate the temperature 10 degrees C, we can reduce the actual time in the chamber, therefore accelerating the aging of the product or package, whatever we're looking at, frame of reference, right? So the accelerated aging factor is made up of these variables right here, the Q10, and that is dependent on the material type, all right? That is defined by your material. You have to actually do the physical testing for that. Now, do we do that for all materials? No, we don't do that for all materials. If I were to ask all of you, like, okay, what do you do for a PET? What do you do for a Tyvek material or something like that? You're not going to have a good answer for me because you actually have to study the material. In the standard, they use a very conservative value of 2. That's the Q10 value, and it's listed in the standard defined as 2, and it is accepted as being a conservative value. Then you have your accelerated aging temperature, which is the temperature at which you're going to age the packaging of the product. And then you have your storage temperature. Now, for me, the storage temperature, they say this is what you anticipate your product to be stored at. And it really doesn't weigh into the equation in my opinion, but it creates this delta that we have. So you could do very conservative, and accelerated aging temperature could be really high, and your room temperature could be really low. And they kind of define some parameters in the standard for us already. Between 20 degrees C and 25 degrees C are typical storage conditions, okay? Are you actually absolutely bound by that? No, you could go outside of that in either direction, but that's generally accepted. 25 degrees C would be very conservative because our delta between accelerated aging temperature, we'll say it's 55 and minus 25, is smaller than if it was 55 and 23 degrees C. And we see this in this example right here. So we have a Q10 of 2, we have an accelerated aging temperature of 55 degrees C, and a real time of 25 degrees C. That yields an accelerated aging factor of 8. So now we have our accelerated aging factor. If we want a real time of 12 months, what should our accelerated aging time be? 12 months, 365 days, divided by our accelerated aging factor gives us about 45.6 days, okay? Now what happens, I'm gonna illustrate the difference between the delta in the temperature. What happens if we go to 23 degrees C? So here we got 46 days, 23 degrees C, we get an accelerated aging factor of 9.2. So you see how our accelerated aging factor went up. Doing the same math, using 9.2 into 365, we get 39.7 days. So we've reduced it by about 6 days. And we round up because we can't accelerate aging if we add a few more hours to it, so we make it 40 days. If we add a few more hours to it, then that's fine, because again, we're aging it artificially. Now let's play with the Q10 factor. What happens if we say the Q10 factor should be 3? We've done our materials study. We decided that we can use 3 for our Q10 factor. If we kept the accelerated aging temperature at plus 55 and the real-time temperature at 25 degrees C, we get an aging factor of 27 degrees. An accelerated aging factor of 27. That's about 3 times higher than our previous example. So when we do that, we can actually age something for 13 and a half days for 12 months. Now, do I say we should do this? No. Let's stick with the standard. Let's stay with conservative results unless you know better. And actually I would encourage that. I always like to say, like, if we could encourage to study the materials a little bit more and increase that aging factor, we could actually do our accelerated aging a lot faster being a shorter period of time than we're currently doing it. So this example, it's about 14 days. So I wanted to just illustrate how fast these numbers can change just by making small changes. So here, there we go. So here is, these are Q10 values found in the standard. So they say 1.8, 2, and 3. 1.8 would be very conservative, and the storage temperature and difference in time for the same 12-month period is about 63 days at 25 and 56 days at 23. And as we keep going up, the time period gets shorter. So just an illustration as to how these factors can make a great difference in our accelerated aging protocol. So when we're developing this protocol, putting everything together, these are the parameters that we're going to define. And we could change this, go to 60 degrees C, right? 60 degrees C is our limit, or in the limit of the standard. It doesn't necessarily have to be your limit, but it's per the standard. Okay, so the takeaway here is before you make any changes to the Q10 value, because we're all excited about, hey, I could get 14 days, right? Materials must be studied, understand the characteristics. identify any nonlinear changes. That's the area where things are responding proportionally, right? We're going through this linear area, and then all of a sudden things get wacky. That's what I mean by nonlinear changes. We look for changes in crystallinity, formation of free radicals, even peroxide degradation in some cases. So now, let's talk about some changes. Can you add humidity? Well, humidity has always been in the F1980 protocol. Okay, it's always been in that appendix back in the back, and I don't think we pay too much attention to it or have paid too much attention to it. So the short answer is yes, we can add humidity. Okay, in fact, we had added humidity long ago. So this is actually coming full circle. Things come in a big cycle. Well, here we're talking about humidity again for the purposes of accelerated aging. So I'm going to be try to help everybody out here by saying, what are you looking at? Are we looking at the package or the product? And if we're looking at, depending on what we're looking at, how much humidity are we going to use, right? What level should that be? Is that 20%? Is that 50%? Is that higher? And also, what are the materials? What kinds of materials are we talking about? And then, of course, ultimately, the acceptance criteria. So for the purposes, again, I guess I'm a little bit ahead of myself here. The focus is on the SBS, or the sterile barrier system, or the product. The materials that we're talking about are polyolefins, can be polyamides, basically materials that are hygroscopic. Materials that want to take up moisture or give up moisture is what we're talking about. So historically, for SBS materials, there should not be a change. We don't have to add humidity to our packaging. So the sterile barrier system, the packaging, materials, we have a lot of historical data, right? We've been doing aging on our packaging for a very long time. All that historical data has meaning, and you should not change your protocol or make any changes based on the new F1980, okay? One key component that came out of this, the changes in the standard, are to add a justification for using uncontrolled relative humidity. So that's where that historical component comes in. I've used it in the past. There aren't any changes. I'm going to continue to use it. And I want to be clear again that the changes are not to change the past studies. That's a lot of change in there. So it's not about the past studies. We're not going to repeat everything. We don't have to go back and revalidate all this stuff. That's not the intent of the changes. So just to be clear, keep everything the same for your packaging materials. Now let's talk about the product. So we have materials in our product, and how this came about is there really isn't an accelerated aging standard for products. So they've incorporated it into this standard, F1980. Now the product can be a whole different ballgame. It can have different types of materials that may be hygroscopic, again, want to accept moisture or release moisture. And to identify those materials, the standard says, well, you can rely on your vendors. Well, that's a heavy lift for your vendors. Are they going to have that data? Are they going to be able to tell you definitively that, yes, this material is not hygroscopic, or this material will not dry out? And then determine whether you're going to want to age with relative humidity. So you're going to want to look at, do I need to add humidity? And this kind of came about with, in terms of the product drying out. So when we have a hygroscopic material, it wants to hold on to water. It's hanging onto the water, and then you put it in an aging environment. Elevated temperature, what's going to happen to the humidity? It's going to drop, okay? So that now starts to pull moisture out of the product. And where you see that turn up are adhesives, things like adhesives, other materials, different types of polymers where you're putting down on the distal end, maybe balloon catheters or something like that. Those are the types of examples of polymers that may be hygroscopic, sensitive to moisture. Okay, so then we're going to determine what that relative humidity should be, at what level, and we can do that using a psychrometric chart. So I'm going to go through a little example about using a psychrometric chart, and this is exactly what it looks like. You got Celsius, you got temperature on the bottom. This is dry bulb temperature, degrees Celsius on the x-axis, and you've got pounds per weight of pounds per mass water on the y-axis, and those lines that are curving up, that's your humidity, your relative humidity. You got 10%, 20%, 30%, all the way up. So if we zoom in just a little bit here, if we look at 20 degrees C, okay, what is the relative humidity if we just increase the temperature uncontrolled? So this is what would actually happen. This happens in our chambers. We see this all the time. Increase the temperature, what happens to the humidity? So we increase our temperature to 50 degrees C, draw a straight line across. So we're at 20 degrees C and 60%. Is that working? No. So at 20 degrees C, we have 60% right here. If we draw a straight line from 60% all the way to 50 and all the way to the y-axis, you see how we're below 10%? Well, that correlates very well with what we see. We record temperature and humidity in our accelerated aging chambers, so you get 50 degrees C with less than 10% RH. So that can be a problem for products. Is it a problem for packages? No. Packaging materials, we've done this many years. Last little point there. All right. So again, product materials, got ahead of myself, talking about polyamides, water-based adhesives, determining the humidity levels, and aging with controlled relative humidity. Now let's take a look at what happens if we increase the humidity. Some of the information in the standard says to use a humidity level between 45 and 55 degrees C at a temperature of plus 50 C. So there's plus 50 C, and the arrow there is pointing to 40%, so we're not even quite yet at 45%. This is our amount of moisture in the air, amount of moisture by weight in the air per volume, and we still need to go up. We still need to go higher. That means we still need to add humidity to the chamber. So the level of humidity that is being suggested is very high. That's my point in bringing this out to the slide. So showing you, illustrating this, is we're down below 10% at uncontrolled levels, but if we artificially increase it, it's going to be a large amount of moisture to add into that chamber. So we need to kind of understand what we're talking about, how much humidity we're going to add, and what parameters we're going to use. And so that's where the relying on the vendors comes in. I'm going to rely on my vendors to give me some information and kind of reach an area where it's at equilibrium, where the moisture is not being added and it's not being actually pulled out of the material. So again, post-test guidance. Sterile barrier systems, the packaging, have been subjected to aging, accelerated or real time, should be evaluated with both physical properties and integrity. So that means that you have your accelerated aging samples and your real-time samples, and at the end of both of those activities, how do we know that nothing has changed for the packaging? So we got to do an integrity test, gross leak, peel are the most popular, seal strength test. And then for the real-time aging, when you're defining your real-time aging, you're going to have a, what is your specification? There isn't a specification. So that's actually a question, what do we do for real-time aging? There isn't any specification. Nobody says you should store your packaging at plus 25 degrees C, plus or minus 5 degrees C. Nothing like that. So you define your parameters. What are your anticipated storage conditions? Would it be 25 degrees C, or is it something different? Is it room temperature controlled, or is it something different? Are you going to account for seasonal temperatures? Our real-time aging storage does have fluctuations with the season. Summer it gets a little bit warmer, winter it gets a little bit cooler. Not much, but it happens, and that's normal real-time information. So it's important to record those conditions, and that's exactly what we do. We record the conditions on a chart recorder. We know exactly what the packages saw during the period of time, and in our case, if you bring the packaging to us, we have control over your samples, right? Your coworker can't just go walking by and pick up some samples because they need some for their study, and so they end up with pilferage at the end of the thing, and you go like, hey, I had 60 samples, now I have 10. What happened? So having a closed system for real-time aging would be desirable. So we have a large capacity for real-time aging, and this is actually the area that we have the storage conditions. Again, recorded conditions, secure, and we have pretty good stability in that overall uniformity and overall temperature stability in the room, real-time aging room. So you determine the needs and the requirements for the materials being tested, packaging, product. Determine your study type and decide whether it's appropriate for your intended purpose. So that mean, again, the product, are we going to elevate the humidity for the product, or are we going to just go with uncontrolled? And once you do that, test parameters are defined by regulatory requirements. That's not anything new. Test selection rationale is important, so I'm going to test it according to this for the packaging. I'm testing it according to this for the product. Defining the acceptance criteria is a question we get asked a lot. It's like, what should my acceptance criteria be? And we can help you define your acceptance criteria, but ultimately, you have a document that has all kinds of different definitions of what the product should be, what levels, with tensile strength, maybe it's torsion, all these other parameters that you're looking at for the actual product. And then what integrity tests are being used. So these are some references that, they're just general references. I'm sure we're all familiar with ISO 11607. ASTM F1980, you see it in all its glory there, -21. That's the latest release as of December. ISO 16775. This is one that I'm not sure a lot of people remember or know about. It used to be the TIR 22, but it's a guidance for the application of ISO 11607, parts 1 and 2. So that helps, that also talks about conducting an aging study only and having a package performance study and having those as separate activities. And of course, right there is Accelerated Aging Time Calculator. That's on our website. You can go there, westpac.com, and click on the resources page, and you'll get the calculators. And we are here at the show, booth 2142, if you'd like to come by and talk a little bit more about this. A little screen cap there of the actual document. If you have any questions, you can always call us. We'll drop into our portal, see us back in the booth there. I have a few cards if you want a card or anything like that. We can talk a little bit briefly here. And we're an independent testing laboratory, medical devices, pharmaceutical, electronics, consumer goods, capital equipment, accredited to ISO 17025, and actually 35 years old this year. So thank you. Any questions? Yes. So the question is that your storage temperature, whatever you label, should be used as your storage temperature on your accelerated aging and for your real time. Yes. So you should, the short answer would be that people are leaning that way, but I disagree with it. I would say that you should test the bounds of that, but you shouldn't necessarily have to actually age it at that particular temperature. You can age it you could age it at that temperature for the entire period, but to have to control that and all that, and really what you should look at are what are the bounds that you need to, that your packaging could be or your product could be subjected to overall. So there's going to be a lower limit and there's going to be an upper limit, right? And then also, if you have accelerated aging data, you've already increased that temperature already. So there isn't any real need because you've already shown that the temperatures you're accelerated aged at 2 have exceeded what your upper, typically it's going to be higher than your upper limit storage temperature. So you've already done it for 46 days or whatever. So I would leverage something like that to say, no, I don't need to store it at the upper limit. CCIT service, we don't have it. Well, we do a dye penetration test for CCIT, but that's the only service we offer. Is the new standard prescribing the relative humidity? And no, it is not. It is making recommendations when you need to use humidity, and that really follows like what materials you're going to use in your product. Again, it's more product focused because the packaging materials are not really sensitive to moisture. So it's not prescribing it, but it's helping you guide. So it's giving you a range, like if you don't know, here's a range of humidity to use, here's a temperature. And if you look at the temperature says 50 degrees C. That's actually the low end of what we have to offer. We constantly, we have plus 50 degrees C, plus 55, and plus 60, because those are the most popular, right? So even at plus 50, you're gonna have a longer time in the chamber. So why not bump it up to 55 degrees C? But then that humidity component, you got to look at that and say, well, do I really want to go to, 55%? That's going to be huge. Maybe I keep it at 45%, something like that. So it gives you a range, and it's not defining it. So that's the key. It's not defining it. It's up to you to define that. Yes. So you don't have to. It's recommended, but again, there isn't a specification that says like, oh, this is a specification. You shall do this. You should have this kind of reporting or anything like that. It's a nice to have, and that's the kind of the bottom line. But there isn't any requirement. So to the point, there isn't any requirement. It's a nice to have at this point. But there's always talk about, oh, we're going to come up with a real-time aging standard, but it hasn't happened yet. All right. Well, thank you for your time today. I appreciate it.